Our presentation will be presented by Ashish John, Charlie Johnston and Errol Solnaki. And today we will be discussing Gauss's law in a uniformly charged non-conducting sphere. Our aim is to determine the electric field both inside and outside the sphere as a function of distance r from the center of the sphere using the ideas of electric flux and Gauss's law.
In physics, Gauss's law, also known as Gauss's flux theorem, which is a law relating the distribution of electrical charge to the resulting electrical field. It is also one of the four fundamentals that governs the behavior of electromagnetic fields that do not vary with time. In terms of what we are actually trying to find out, we need to understand what Gaussian surface is and therefore how an electrical charge is distributed.
A Gaussian surface is a completely closed surface in our experiment. A sphere with the flux of a vector field is calculated. The electric flux through a flat object area is defined as electric field times the component of the area perpendicular to the field. If the area is a 3D object such as the sphere, then the evaluation of the flux generally requires an area integral since the angle will be continually changing.
Gauss's law also claims that the electric flux through an enclosed surface is equal to the enclosed charge divided by the epsilon naught. The epsilon naught is the permittivity of free space, where epsilon naught is equal to 8.55 times 10 to the negative 12 coulombs squared divided by Newton meters squared.
Conceptually expanding on this, it means that if you take a positive charge and place it in an enclosed surface, the positively charged particle will radiate electrical fields outwardly from inside of the surface. Therefore, the same electrical field will ultimately penetrate through the enclosed surface. And if we take the change in area, dA, as pointing outwards, it demonstrates that the electrical field will also somewhat be directed in the position of dA. Therefore, the electrical field lines going out of the surface will be counted as positive.
That is why we get the formula of the integration of E dot dA, which is Q enclosed divided by the epsilon naught.
When dealing with non-conductive spheres in Gauss's law, you can calculate the flux and the electric field at any point in various other ways. The circle here is a cross-section view of an insulated sphere, within which there are charged particles. The magnitude of the electric field due to the charged particle would be different at different points, both within and outside of the sphere. Using mathematical calculations and Gauss's law, general equations can be derived to aid in determining this electric field strength.
First, let's look at the charge that would be given at any point within the insulated sphere. Obviously, the sphere itself has a radius, which we'll denote as r. And since the sphere both has volume V and a charge Q, we can create an equation for the charge density ρ for any given sphere to be ρ equals to charge over volume, which is Q over V. And thus, if we rearrange this formula, the charge can be found by multiplying the charge density by the volume. So Q equals to ρ times V.
Moving on, let's suppose we want to find the electric field at distance x from the charge. Remember that x is less than r. Since the electric field will be the same at every point, that is x units from the charge in the center, we can draw a Gaussian sphere to indicate the fields at their points. The Gaussian sphere will have a radius of x units. The drawing of the cross-section of both the spheres is shown.
As mentioned above, Gauss's law also claims that the electric flux through an enclosed surface is equal to the enclosed charge divided by the epsilon naught. Using this equation, we can calculate the electric field strength at point x. Q enclosed is the charge enclosed by the smaller sphere in this instance, and since Q equals P times V, we can replace the Q enclosed with pi times P. Therefore, Q enclosed equals 4 on 3 pi x cubed P.
Now looking into the closed surface integral of Gauss's law, we remove the electrical field strength P numeral E from the integral. This is because of the symmetrical property of the sphere, meaning that the E value would be same at every point on the surface of the inner sphere. The dA in the integral represents the sum of every point through which the field line passes. We can substitute this with the value of the surface area of the Gaussian sphere, which is 4 pi r squared. In these terms, the radius is obviously x, so 4 pi x squared.
Substituting the derived equation into the original Gaussian equation, we can get the following. And by simplifying and rearranging the equations, we can find the electric charge strength of charge at point x from the center of the sphere.
This equation to obtain the electric field at any point within an insulator represents as a linear equation. This is because all the values on the right-hand side of the equation are constant except for x, which here is the independent variable of the equation. The electric field E is dependent on x. The graph of E versus x would look as follows.
The linear graph indicates that as you go further away from the charge inside an insulated sphere, the electrical field strength increases. By analyzing the graph, we also see that the maximum electrical field strength is present at the inner surface of the insulated sphere. This is denoted by R in the graph. When measuring the electrical strength outside the sphere, the graph varies. We'll prove this by further calculations.
In order to understand and measure the electric field strength of a charge outside of an insulated sphere, first we'll draw another diagram that will illustrate the new scenario.
In this case, the inner circle is the insulated sphere carrying the charge, and the largest circle symbolizes the Gaussian sphere present y units away from the charge. Bring down the Gauss's law again to calculate the electric field. There are some slight variations to the equations.
The Q enclosed in this circumstance is the charge enclosed by the insulated sphere itself. Hence, Q enclosed would be 4 pi r cubed rho. The integral of Gauss's law changes like before, but we replace the x with y, as the radius here we assume is y. So thus, the integral equals the charge times 4 pi y squared. This equation, we can determine the electrical field of a charge measured from outside from a sphere. The equation is as follows. E is equal to r cubed over r cubed times rho over 3 times absolute naught times y squared.
The final equation we obtain here is not a linear graph, but instead more of a part of a truncus graph, 1 over y squared. All other pronumerals on the right hand side besides y are constant. Even the r value is regarded as constant, because the radius of the insulated sphere is unchanged throughout. If we plot this new function with the graph above, we get the following.
From this graph, we can comprehend that as you move away from the sphere, the electric field strength decreases outside the insulator. This means that theoretically, no matter how far you measure the electric field of the charge, there will always be some kind of field and never be zero. This is because of the 1 divided by y squared graph never equates to 0, but obviously after a certain point, the electric field is so small in size that it is negligible and can be regarded as 0.
When it comes to choosing which equation to use to find the electrical field strength, the following can be done. First, measure the radius r of the sphere and know the distance d from which you want to measure. If d is less than r, use the first equation derived as the flux enclosed will be equal to or smaller than the imaginary Gaussian sphere within. But if the distance is greater than r, the second derived equation can be used.